covariance matrix. So by looking at that, if we implemented the whole system in hardware, we're going to get a 64 times faster system compared to what we have in the hybrid implementation. So looking at future work, we're going to do rigorous testing using signal generator setup, angle sweeps, and single versus multiple signals. Also, we need to do anechoic chamber testing with the rest of the system with the translation board that was designed by Ahmed. And to look at SNR effects in different IF frequencies. Also, need to implement more DOA estimation algorithms using the hybrid platform, such as Esprit or Music, since it's ready to implement those systems. Conclusion, we looked at the Bartlett DOA estimation. It was implemented in custom hardware, in soft processor, and hybrid. Advantages of each technique. Custom HDL provides increased performance. Software implementation reduces development time. A hybrid approach minimizes critical path circuitry and balances between the custom hardware and the software. And also using IP, Xilinx IP cores alleviates some of the development times. And then looked at MPDR estimation implementation. Looked at the performance, the development time, and the resource utilization. I'd like to thank my committee members, Dr. Brock Lemers, chair, and he's my main advisor, for all the help that he provided, especially in the last semester. He's been helping a lot in getting the system done. And Dr. Ikon Huang for helping with the algorithms and to understand each algorithm, DOA algorithm. Dr. Richard Wolf and Mr. Andy Olson. Also, special thanks to Advanced Acoustic Concepts for funding this project, and for the ACE department for providing a healthy environment for us students. I bet everybody agrees, right? And the research group, Aaron, he designed the analog to digital converter board, and Ahmed, he helped me in understanding some of the algorithms, also understand how the translation board works. Ray Weber for building the system, the test bed setup for consisting of the signal generators, and Sam Harkness for developing the great FFT implementation on software. Thank you. All right. Yeah. Bartlett?
Yeah, so great.
Yeah, well, Bartlett implementation, well, it's kind of special because it was the process when I was learning still about the system and learning how about implementing on FPGAs. So it was the longest period, basically. It took maybe 8 months in order to complete the hardware implementation of Bartlett. But the software implementation, it was only 1 week or 2 weeks just to get, I mean, it took Sam to, like, the FFT was the major thing to be implemented. It was during the summer, I think. But to implement the DOA itself, it was just a matter of reading MATLAB code and just write it again in C code. So it's it didn't take like a week or something.
Can you give an estimation for how long it will take for MPDR to implement it?
On hardware? If the system designed for the covariance matrix was used to implement the computation of the power, the spectrum, there are 2 ways to do it. If it's going to be straightforward, just cycle through the data and do multiplication. I kind of remember maybe in Bartlett when I did in hardware it took like 2 weeks or something, but Bartlett is simple. So I would say to finish that maybe like 2 months or something like that, maybe, or something. Yeah, it depends on really like the devil is in the details. So you would think it would take 2 months in general, but all these problems and signals, like because it's really hard also to look at the signals inside using the chip scope. Literally, I have to sit for 15 minutes until the whole system is synthesized and ready to test every time I do any little change. So, but in the processor, any change you do, you just compile it quickly for a few seconds and then ready to implement. So it would, yeah, I would think maybe a few months to finish the whole system hardware.
2 months for somebody who spent 2 years learning it.
Yeah, so you need somebody who
2 years.
Yeah, but
I would say.
yeah, yeah.
Does everything in the processor happen sequentially? Is that why it's a slower process?
Yeah,
So
and
has anyone maybe thought of another new project being multiple micro
yeah,
base
well,
cores and
yeah.
then being able to pipeline those cores together?
yeah, that would be a good idea. The problem though is that this current FPGA that we have, if we want to implement 2 microblaze processors, I mean, I think in other, like Flint Gower was doing research and he managed to get what, 4 microblazes?
5 on there.
5? Yeah, but that's without anything else, maybe just small state machines. But with the FFT, the hardware FFTs, the main problem is the extreme DSP slices and the memory blocks in the FPGA. Those are the most expensive parts. And then these are consumed heavily with the microblaze. I think the microblaze uses 32, each microblaze uses 32 blocks of memory. And then the FFTs, they use 72 DSP blocks and like 20 memory blocks. So fitting all that together, maybe there's a chance to fit another microblaze, but it will be hard to fit, for example, more than one. Like, it will be really hard. Or if you move into like a huge FPGA.
Is that PowerPC on that one chip?
I don't know. I think the one I'm using, it has a PowerPC on there, but we didn't look at the. Basically, I think the boards that we have here, not all of them, they have PowerPC, so we focused on the microblaze. Yeah.
You talk about using chip scope. When you use it, do you incur penalty performance for having it there?
It affects the overall. For example, when I finish synthesizing and implementing, it tells me how fast the system can operate at. So I had this problem with when I sped up the ADC board. When it was running at 12.5 megasamples per second, I was receiving data at as fast as 100 megabits per second. So I was able to get that on my 100 megahertz clock speed. But in order to speed up the ADC board, I had to pump up the speed to 200 for only the ADC driver. But in order to test that, if it's working or not, I have to implement a chip scope. And then whenever I implement that, it drops the maximum speed in run at to 160 megahertz. So I had this problem occurring. But as an overall, yeah, it affects, but not if I'm running on the other parts, since they're all running at 100 megahertz, the chip scope wouldn't occur any sort of delay or degradation in performance. Yeah.
I've got a signal processing question.
Okay.
So ultimately, the output of this whole system is one of 8 numbers. Is that true? You get 8 directions.
Oh well, for the Bartlett, the way we implemented it, yeah, getting only 8 directions. We can. That's just to prove the concept. But for MVDR, we're getting 360 directions. So.
Well, the question is, it seems like if in the Bartlett example, you're doing a lot more work than you really need. If your resolution only needs to be 8 out of 25 megahertz, you could do a subband approach with 8 filters and then be done. Mm-hmm. Or you do a sampling at the same data rate with maybe a length 16 FFT. And again, everything about it would be shrunk substantially. So I'm wondering if you could help out here a little bit by thinking end to end. Do you really need a 1024 length
FFT?
Do you really need it to be complex? It doesn't seem like it. Are there other algorithms that you can choose that would just fundamentally be a 10th or a 100th of the computation and still give you the information?
Yeah, I'm trying to think of the answer here. Well, first thing, for Bartlett, the reason we did 8 is to prove the concept, but for, like the system is designed